This is one of the coldest places on Earth. And this is one of the coldest places in the galaxy. This is the hottest place in the solar system. And this is one of the hottest places in the universe. A vacuum, emptier than outer space. The largest number of high-tech magnets ever built. The largest, most complex electronic instrument on the planet. It fills much of the Geneva countryside, but you can't see it, even if you look for it, because to find it, you have to go deep underground. At 100 meters depth, housed in a 27-kilometer long tunnel, the Large Hadron Collider is ready to start.
Although this looks like a giant gas pipeline, this machine is the most powerful particle accelerator in the world. And in fact, it uses the most sophisticated technologies available to us today. More than 9,000 magnets guide two beams of protons in a circular path through the accelerator, and then accelerate them to speeds approaching the speed of light. And then the beams crash together with as much energy as a high-speed train.
We can make two objects collide at a very high energy and make a new object of mass which equals the energy total of these things that have collided, which is going to last for very little, and you're going to discover it by making it.
Every second, 2 billion protons smash against each other inside the LHC and recreate the conditions that were present less than a billionth of a second after the Big Bang. This is when the universe started, in a massive explosion of pure primordial energy.
What's really exciting about this is that some of these new objects or particles are very different to the particles we originally collided together. In fact, they're particles that we no longer see in the world around us. But although these new particles only lived for a short time around the start of the universe, they played a fundamental role in making the universe look the way it does today.
If we want to understand the origin of the universe, one of the ingredients that we need to understand is these particles that last so little and that you cannot find now in mines because they have disintegrated completely from the origin of the universe.
The more we study it, the deeper we look into things, the more we find there is to find out. Because there are some very strange mysteries in the universe.
We know that mass can turn into energy, but we don't know how that happens. We know that back a millionth of a second after the Big Bang, matter didn't exist in the form of protons and neutrons, but in a completely different state. And we know that gravity was extremely important back in those earliest times, but we don't know exactly how it works. Maybe the reality out there is much closer to science fiction than the real world.
The LHC is like a spacecraft venturing into the unknown, looking for answers to these questions. And 4 major experiments called Atlas, Alice, CMS and LHCb have built gigantic detectors on the LHC ring to capture the instant of particle collisions. We're going to use them to find out more about the mysteries of the universe. On a clear night, we can see thousands of stars, but all this stuff we can see or detect only accounts for 4% of the whole universe. The rest is made of dark matter and dark energy.
If the universe was filled with only the matter that we're familiar with, what we can see with our own eyes when we look out in the universe, galaxies and clusters of galaxies wouldn't move, rotate and turn the way astronomers see them today.
We believe that there is something else out there that is modifying their movement, but at the moment we cannot see or detect what that something else is.
So there is a theory which could actually explain dark matter, and this theory is called supersymmetry. So according to supersymmetry, for each particle we see, there is another particle which is sometimes called its supersymmetric partner. One of these supersymmetric particles could perfectly be the particle which makes up dark matter.
If these supersymmetric particles exist, then the two largest experiments, ATLAS and CMS, will find them. But dark matter isn't the only thing we don't understand.
Antimatter and matter were created in equal amounts at the very birth of the universe. However, we also know that when antimatter and matter come in contact with each other, they annihilate, we say. They destroy each other and they vanish into pure energy. The LHC detector is a precision instrument with which we will try and unravel the true nature of this mechanism.
The idea here in the ALICE experiment is to use the LHC to recreate such high temperature conditions as were prevalent in those first instants of life of the universe, which should allow us to recreate tiny droplets of primordial matter in order to study its properties.
The vacuum is a substance, and like any other substance, you can make it vibrate. And the vibrations of the vacuum are called Higgs particles, and that is the object we are most trying to find at the LHC. The Higgs particle is essential to theoretical physics because it's different from any other we have discovered so far. It is the one responsible for the masses of all other particles.
These detectors have been designed to look for the Higgs particle, but what if we don't see it?
That would be fantastic, because it would mean that we really haven't understood anything. And this is the best situation in science. The one that precedes big revolutions is when we realize that we have actually understood nothing.
It might be that reality is very different to this three-dimensional view of the universe, and that'd be really mind-blowing.
There is another theory which is called the string theory, whose aim is actually to unify all these particles that we see in a single framework. So according to string theory, all particles are different vibration modes of a single fundamental object which is a vibrating string. One of the surprising consequences of string theory is that you reach the conclusion that there have to be extra dimensions in the universe.
If the LHC is lucky enough to penetrate with its very high energy inside these points that contain extra dimensions, then a complete new field opens up of possible new discoveries.
You're looking at 12,000 tons of metal and electronics, which have been put together with a precision of 5 microns. That's 5,000ths of a millimeter. And it's taken many companies, hundreds of universities and research institutes, and thousands of scientists and engineers to put these precision instruments together.
The detectors like CMS and ATLAS arguably constitute the most complicated apparatus that science has ever seen.
The LHC and its detectors will produce billions of interesting events every month, but we'll need the computing power of the grid to tell us what we found.
There could be some big discovery about the nature of space-time, or just what's really out there, what's fundamentally there.
We could make a complete series of new particles. We could make wormholes, which are little holes in space-time in which you can go from one point in space and time to another point in space and time, so that you could travel to another time.
Scientific research is an exciting trip with a fuzzy map and an unknown destination. We are a bit like old-time explorers. We know there's a lot out there to discover, but if we knew exactly how and when we will discover it, it wouldn't be research.
And research is the driving force behind the world we live in, because none of the things that we enjoy would exist without the fundamental research that's gone on into electricity, into magnetism and nuclear physics over the past 2 centuries. No amount of applied research on the candle, for example, would have given us the electric light. Science needs space for creativity and imagination. And the LHC is going to take us onto a journey into the unknown.
Words are flowing out like endless rain into a paper cup. They slither while they pass, they slip away across the universe. Pools of sorrow, waves of joy are drifting through my open mind, possessing and caressing